So to turn what I've written so far into a function which I can easily modify and change and play around with, there's a few things I need to do. I need to define what the inputs to the function is going to be. I need to define how the function is going to work, and I need to define what the outputs of those function is likely to be. One of the really nice things about functions in R is when you create your own function, it works in exactly the same way as all the other functions that you use in R. And if you want to turn it into something which other people can use as well, you can even build your own package. All of those packages were just built by people who had an idea for a useful function and went about creating it and sharing it with everybody else one day. Maybe there's a demand for a simulation function for the birthday problem if one does not already exist. And it all starts with the same simple process. So I first of all need a name for my function. I guess I'm going to call it birthday problem. And I need to assign it to be a function. And again, you see function is a special function within R. It's another control flow function. So how this works is the arguments that we put within the round brackets here are the arguments we want to have available for our birthday problem function. So here, I think there's maybe 3 things, but to begin with, I'm just going to pick on 2 of them. I want to set the number of iterations, and I want to set the number of people which are present in the birthday party or room where there are things happening. So I'm going to have an argument called people, and I'm going to have an argument called iterations. And then again, outside the round brackets, we need the curly brackets, and the curly brackets need to contain everything which is going into that function. So similar to how we split it out with the for loop, within the function, we need to have the braces, and within inside those braces is all the code which is running as part of that function. Note that we've now got a nested set of curly brackets. We need to make sure we know which one refers to which other one. It's not necessarily as straightforward when it's all on the same line when it's round brackets for a single function. So RStudio does try to help you out by highlighting the closed brackets to the open bracket. You can also collapse sections. You can see if there's a little tiny arrow whenever you've got a brace open, which sometimes helps with navigation and finding the relevant bits at the start and the end of the code if you've got lots of nesting involved. So within this function now, do we need to make changes to the code? Yes, so we need to update it so that we use the arguments which we've got going in here. So people refers to this 23 here. So instead of 23, I'm going to put people. And this works like a temporary object again. Like if we had an object called people which took the value 23, outside of a function, this code would work in the same way it has been already. And when we have an argument, we define the argument, this kind of effectively creates that temporary object called people. And that's the only time we use the number of people in the code. The iterations we use a few times because we use it to set up the size of our data frame, we use it here in our for loop, and we use it again when calculating our standard error. So we need to make sure we hit on all those different times that we use it. The other thing that we might want to do is set default values. So for the number of people at the party, I'm not sure there's necessarily a sensible number of people that should be a default. For the number of iterations, maybe let's set this at 10,000. It seemed to run relatively quickly. We got a reasonably small standard error as a result of doing that. Doesn't seem like an unreasonable default. We don't want to specify the number of iterations every time, but it's nice to be able to change it if we do want to specify it. The final thing that we have to think about is what is the function going to return at the end? So in our code, we've got this summary at the end. I think there's a couple of extra things we might want to put in the summary. We might want to repeat back the number of people. So people equals people and iterations equals iterations. Just to include that information in the output could be quite useful. And I'm also going to then take the very final step where we need to explicitly say it's this object that we want to return. So we can pipe from our matches data frame, which then gets summarized to lesser proportion matched and the standard error. And we can then pipe that into the return to say this is the output that we want from our function. So if I now run this piece of code, I see nothing, except a function has appeared in my environment, but I get no output because I'm just defining a function at this stage. I'm not calling that function, I'm not looking at the results from running that function, but I can now use my new birthday problem function. Let's run it for a number of people equals 23. So as you've probably seen in R, you could write people equals 23, or based on the position of the arguments, I could just write 23 because it automatically assumes this is the first argument, people. So if I now press run, I got a proportion of 0.5057, and you can see if I run it lots of times, with my 10,000 iterations, it's relatively stable. I can now do something different with my iterations. Maybe let's just go for 10 and see what happens. And we should be seeing something very unstable. You can see, yeah, 0.2, 0.6, 0.4, 0.6, 0.8. It's jumping all over the place. So 10 iterations, probably not a good idea. Let's get rid of it again. And I can easily now say, okay, what happens if I have 100 people in my party? What's the likelihood of having a match in the birthdays? And this time, oh, it's 1. Pretty much when you get, I think, over about 75, your likelihood that there will be 2 or more people in the party with a shared birthday gets to sort of 99.9%. You can see this time with 75 people, I think 1 of my 10,000 iterations there must have been a match. Again, this time 1 out of my 10,000 iterations there was a match. Very, very small numbers here where you find matches when you get over 75 or 80, for example. So now I'm pretty pleased with my function. It seems to be quite functional for solving this birthday party problem. The next step is going to be, how can I now bring in this element of having different birthdays? So on the website, which I mentioned before from the Office of National Statistics, has this interactive analysis of all the different birthdays in the year and the different probabilities of being born on those particular days. And they actually include this button here where you can download all of the raw data directly. And it's quite nice that they just leave their data lying around for you to use in statistical videos like this. And it's quite nice, if you copy that link, you can read this in directly into R without actually having to download the file separately, because there's a nice URL which is easily accessible here. So a little nice trick. Again, I wouldn't necessarily recommend this all the time because you probably want to have a static version maybe on your computer, but if it's a data set which is always stored in the same place and is regularly updated, it can be a nice thing here to read this in directly from the URL. And so what we can do is we can put in the URL instead of the file location, as long as we wrap it in the URL function itself. So if I run this bit of code here, what we can see is we have a data frame which has all of the days of the year and tells us the average number of births on that particular day of the year. There's one thing to look at here which is going to be necessary when I'm testing this assumption here. How much does it matter that we've got more births on some days than another when looking at my simulations? And that's thinking about the 29th of February. Because on average, there are 1,788 births on the 29th of February, but this only comes around once every 4 years. So what I want to do is either divide that by 4 or multiply everything else by 4 so that I've got the ratio of birthdays roughly correct here when I'm thinking about moving to my next step. Because I want to have the right rough proportions for every day of the year. So what I am going to do is I'm going to pipe here into the mutate function, and I'm going to create a new column called ratio. And in this column called ratio, I'm going to say if else, and if the date is equal to the 29th of February, then this value is going to be the average divided by 4. Otherwise, it's going to be the average. So if I run this now, I have a new column called ratio. Nearly every day of the year, this is going to look the same. Hopefully once I get to the 29th of February, I missed it. Where's it gone? That page. You can now see the 29th of February, the ratio is lower. So I have now the data which has the correct, for the UK context at least, likelihood of different birthdays in relation to each other. It's not 1 to 1 to 1 to 1. I'm going to save this as a data frame. I'll call this UK births. You can see this is now popped up in my environment. So now to apply this into my function, I need to go back to the sample function before. Because again, one of the default elements, which I ignored the first time around when I used the sample function, was the probability that each element is selected. And by default, this is that every item is equally likely, which is a pretty sensible default in this case. But if I want to modify that default, this is the prob argument. And conveniently, I happen to have a column within my UK births data frame which already has the ratio of births to each other. One thing that sometimes catches people out about this sample function is it doesn't actually need to be probabilities in the prob function. Proportions or ratios or relative weights is totally fine here. It will do that standardization process for you. So if there is a value of 144 versus 400, it will convert that into a ratio which will sum to 1 if you like. So it doesn't matter that these aren't probabilities, instead they're ratios. It will work that out for you. So what I want here is a column called ratio. So here, this will give me an error because people only exists when I run my function. It's a temporary variable which only exists inside that function. So right now, there is nothing in my environment called people. So I need to make sure when I'm testing this change that I put in a number, like for example, 23. And visually, it will not really be possible to tell too much whether or not this has made any change. I promise it has. If we really want to see this prob function in action, maybe we can change it to be something really stupid. So let's say, for example, that the first day of the year has a relative likelihood of 1,000, and then the remaining 365 days of the year have a relative likelihood of 1. And this is where I might want to use the rep function. I'm going to repeat 1 365 times. Because for the prob argument to work, it needs to be the same length as the list of things which I'm sampling from, my X unit here in the sample. So I need to make sure I have 366 values to give it. So let's try this now. And you should see now when I have a relative likelihood of 1,000 for day 1 of the year versus 1 for every other day of the year, lots and lots and lots of 1s get sampled. This is not a reasonable distribution of birthdays. We don't have thousands and thousands of people born on January the 1st and nobody born on any other day of the year. But this ratio of birthdays here from the UK data looks pretty good to me. So let's go back to our function here. And we need to add in an extra argument here, which is, let's call this probabilities. And I think this makes sense to have a default, and I think the equal likelihood of each birthday as a default makes sense. So we can't just write prob equals 1 in the sample function, it needs to be again 366 items. So we need to write rep 1 366 to repeat 1 366 times. All days are equally likely. And then in the sample function, I could set my argument prob in the sample function to be my newly defined argument here, probabilities. So again, I've set this as a default function, so I don't need to specify it. If I run here with 80 people, the same thing that happened before should happen. It shouldn't be any different. But I can now, if I run it in a sensible order, so I'm going to move this down to beneath where I have read in the data. It won't make any difference now because I've already read the data in, but in future, if I wanted to use this data, I need to think about my sequencing. So I'm going to put in here UK births dollar ratio. This again is not going to work at this point because that's the third argument. So this time I do need to name it by saying probabilities is what I called it. Probabilities? No. Probabilities. And now, if I spelled probabilities correct, I'm questioning if I have. No, I have. Phew. It's now using that new probabilities from the UK data. So let's move back to 23 people. This is where we think it's 50-50 when we have equal birthdays. And you can see it still looks like 50-50. let's just take a look at the two things side by side perhaps. Let's have one without the different ratios and one with the different ratios. And you can see my differences when I do 10,000 iterations, 0.51, 0.51 to to 2 decimal places, kind of the same. Really looks like those people who say this doesn't really matter and it's a good assumption, they might be onto something here. It might not really make too much impact, all of these different allocated birthdays. I might have gone down a bit of a wild goose chase and found that everything is actually the same, all the assumptions check out. Could just be a coincidence though. What if when I go to 10 instead of 23, there's maybe more of a difference at the lower end of the range or at the upper end of the range. It's just in the middle where they converge together. So let's take a look at 10 birthdays, 10 people in the room. Again, 0.11, 0.12. Getting similar, maybe a bit different, but hard to tell whether or not this is having much of an impact. I think just to really see if there is an impact, what I'm going to do is I'm going to finish off by looking at the full range of number of people. And I'm going to look at a slightly different way of iteration. So I've already looked at iterating with a for loop. There's another way that we can iterate in R, which is perhaps a more modern way. It's part of the tidyverse. So everything you're seeing so far with the way that we've defined the for loop and the function, you've possibly noticed, other than a few bits I put in, it doesn't look very tidy, all these brackets going in. There's lots of disparate elements and no piping. So there is this alternative way of trying to do some of this iteration in R, which comes from the per library, which is part of tidyverse, and the key workhorse function behind that is map. So map is a function which lets us iterate over a sequence in a slightly different way. So this time, I'm going to take the values of 1 to 100, but I'm not going to think of these as iterations. I'm going to think of actually, I care about the values 1 to 100 here, because I want to map these onto my birthday problem function and map it for what happens if there's 1 person, 2 people, 3 people, 4 people, and so on. So if I pipe from 1 to 100 into map, then I can define the function I want to map, so birthday problem. And what will happen is the first argument of that function, which is people, will inherit the first value 1, then the value 2, then the value 3, then the value 4, and so on. And it will take the default values of the other arguments within there. So if we run this, it will take a little bit of time this time because it's not just running 10,000 iterations, it's running 10,000 iterations 100 times. So you saw it took maybe a split second to do 10,000 iterations once. That can add up if you're doing that over a sequence here. So you can see here, I'm killing for time while this is going through. I'm just going to prepare a little bit in advance while that's running by setting up the code for having the alternative with the UK ratios of probabilities in here. There we go, it's come through. You'll see with map a couple of things now. Firstly, perhaps the most important thing that we see is we've got a whole lot of output here because we get one object for each of our mapped elements. So if we click on any of them, we can kind of see, okay, this was 77 people, this was 65 people, this was 52 people, and so on. So what we actually perhaps want here is not map. So this can be useful if the output we get from our function is not a data frame, and it would be very incompatible to link them all together. So what I'm going to have instead is map df, which will bind together all of the output into a data frame. The second thing I'm going to do is I'm going to store this as an object, because it took a bit of time to run, and now this is just temporary output. So this is equal birthdays. The final thing I'm going to do is I'm also going to reduce the number of iterations. So this runs a little bit quicker next time. So it may not be as precise, but for pulling out all the data, and I'm going to pipe it into a graph in the end, just so I can visually compare the two side by side, I'm going to set the number of iterations to be just 1,000 instead. It's not going to be perfect, it's going to be a bit spiky, but it's going to be enough to give us an idea of what's going on. And hopefully this time it should run much quicker. as it has, and we can see we've now got a data frame created called equal birthdays, which cycles through our number of people, and we can see our proportion matched every time. So now let's do exactly the same thing for our non-equal birthdays. So let's call this real birthdays. And again, I'm going to add in the argument for prob UK, and it should actually be probability UK births equals ratio. So I'm going to steal it from there. Always copy and paste the right thing when you're working in R. So let me now run this chunk of code, if I can click on the right place on my screen. And you can see I've now got my real birthdays as well. So here we go with our real birthdays. It's a very similar looking data frame. So from these simulations, let's now compare them side by side. Let's really use the power of R, one of those great elements of R, which is ggplot, by making a nice visualization of these results. I could merge these two data frames together. For the graph I want to do now, I don't think I need to. I'll start out with my equal birthdays data frame. I'm going to have on my y-axis the match argument, which I believe is what it's called. Let me double check in the data frame. Proportion matched, always good to check. Proportion underscore matched. And on the x-axis is going to be the number of people. And I am going to have a red line for the equal birthday probabilities. So you can see here we go from our 0 to 100 people when we assume all birthdays are equally likely. You can see it gets a little bit spiky in places because we only did 1,000 iterations. But this is the curve as we go through. We find the point where it meets 50%. Unsurprisingly, at this point, it hits 23 people. And what we can do here is add in another line, and this time it's going to be blue. And one of the nice things is you can set data within the geoms. Often don't see people doing this too often. It means you get a bit less flexibility over the appearance and so on, but for just making a quick graph, it can be easier than merging things together. So if we bring in our real birthdays data, you can see this has now got a blue line. Because I've got exactly the same columns in here, the aesthetics are actually carried forward into that new data frame. So it's pretty easy to have a nice standard format here. But ultimately, our conclusion here is those two lines are basically on top of each other. This impact of having real birthdays distributed unevenly throughout the year versus making that assumption that all birthdays are equally likely has almost no impact at all on the results of the birthday problem. And theoretically, this is what people have always said in papers, that this assumption kind of doesn't matter. So we have learned something here. We've learned that testing out these assumptions actually is not too difficult in R. We've got the flexibility to actually explore this. Understanding the maths behind why this doesn't make any difference is super complex. There's a couple of papers referenced below, and as you saw in the introduction, they're talking about simulating things for 10 to 20 years, 10 to 20 centuries, I should say, for just solving this mathematically and proving it beyond any reasonable doubt through the theory alone. Through the simulations, we got there in about 20 minutes. And making further modifications to this is going to be really easy and really flexible. Once you set up this framework for simulations, it can link into ggplot, it can link into the modeling functions. Using R gives you so many options with simulations that you just don't get from either standard statistical software or other programming languages. You've got so much power to really explore your data in many interesting and unexpected ways.